guys, welcome back. So today we're going to be talking about pH curves, buffer solutions, and buffer solutions. So firstly, let's start with what even is a pH curve. Now a pH curve is essentially a graph that has pH on the y-axis and the volume of a titrant on the x-axis. So it's a graph of titrant volume versus the pH of the solution in the analyte. Now there are many different types of pH curves. Only really four of which you're expected to know. Strong acid with strong base with strong acid, weak acid with strong base, and weak base with strong acid. So the top four here. Now, generally they all take the form of this sort of S shape. They take the form of this S shape. And some features to note here is that for strong acids and strong bases, here the line is quite flat, and then all of a sudden it gets super steep, and then all of a sudden it gets flat again, where it asymptotes to the pH of the initial base. Since as you essentially add infinite volume, you assume that the acid in there basically didn't exist, and it essentially, as you go into infinity, it just reaches the pH of whatever your titrant was. And similarly here at the very start, it's just the pH of whatever solution that the analyte is. And similarly here, and then as you add more and more titrant into it, the pH, gradually, like very, very, very gradually increases or decreases depending on if you're adding acid to base to acid, or acid to base. And then all of a sudden, right before the equivalence point, right around the equivalent point, there is a very, very sharp change. Now, the inflection point, the point of inflection where the concavity of the graph changes from concave up to concave down, that's actually where the equivalence point is, where that point of inflection is. And we can see here that at pH 7, for a strong acid and base pair, that inflection point will always lie at a pH of 7. Now, what about for a weak acid? What about for a weak acid strong base curve? They look similar, except here there's a few slight differences. First here, notice this slight jump here, and then notice this region of relatively constant pH. This is actually called the buffer region, and we'll go into the chemistry of that quite soon, but notice here that the pH here is relatively constant. Here as well, you can notice that the pH is relatively constant, but notice here how it takes quite a bit of effort to get it to finally go to the pH of 7. This is technically known as the buffer region as well, but you're generally going to come into it in the context of weak acid strong base, or weak base strong acid, or whatever. There's weak and strong of something. And then you get the pH of the equivalence point, which is greater than 7, since the conjugate base that forms the salt does have acid-base properties, so it does affect the pH of the equivalence point. And you'll notice here that this half equivalence point here is marked, and this is actually where the pH where it equals the pKa of the acid. Again, when you go into discussing buffer solutions, this becomes important. And similarly, this half equivalence point here is also significant for weak acid and strong base, or weak base with strong acid. The idea here is that pKa is what's at play here. I'm going to show the other curves here. You don't have to know these for IB, but here it's similar sort of idea, except it's at 2 times the volume equivalence point, where you get pKb, where you isolate for pKb, and similarly pKa. Well, here it's pK, 2 volume equivalence point is pKa, and then here you have a weak acid, weak base, and here that's just sort of the graph of that. A couple of things that you'll be asked to let's sort of describe the shape of pH curve. So if you're starting at a strong acid or a base in the flask, you will have an extreme pH, where extreme pH is a pH of less than 2 or greater than 12, and there's a very gradual change in pH. And if there's a weak acid in the base, it starts at a moderate pH with an early steep slope before flattening. And regardless of the strength of the titrant, um, the curve ends at an asymptote. And for a strong titrant, it extends at a pH, and with a weak titrant, it asymptotes at a moderate pH. And then the delta pH, is the derivative of pH with respect to volume, is the steep part of the curve, is the sort of slope of the how much it's changing by how much the pH is changing by when you add volume, and where that slope is at its maximum, that's where the equivalent point is. The equivalence point is. And the pH of the equivalence point depends on what the products of the reaction are. So here it's 7. Here we have to use the properties of acid base. We have to use our properties here. We know that this is a weak acid. This is a strong base. We know that this is neutral, and we know that since these are conjugates and this is a weak acid, its conjugate weak base does have significant acid-base properties, and since it's a base, it is a pH that's greater than 7, and similar sort of logic can be used to deduce that the pH is less than 7 here. Strong acid, weak base. And these two conjugates are both weak. Ka times Kb equals Kw, and since we know that Ka is very small here, Kb is very small, Ka must be small as well. However, it must be larger than Kw, so therefore it will affect the acid-base properties of the solution. And therefore, since this is a weak acid, it's less than 7. Now, I mentioned some talk about buffers before. Now, let's actually go into explaining what a buffer is. A buffer is a solution that maintains a relatively constant pH despite the addition of strong acid or strong base. Note here that you can only change the H plus or OH concentration to it slightly, and if you add enough acid or base, you can actually exceed the buffer capacity of the solution, and it'll go haywire. A buffer is a mixture of weak acid and its conjugate weak base in nearly equal quantities. That's what in the context of IB, that's what it means. So one way you can get a buffer, I should say, is that you can have a weak acid and its conjugate weak base in nearly equal quantities. This is because Ka times Kb equals Kw. However, since for a weak acid, Ka is somewhat small, Kb is also somewhat small, and therefore, since they have similar effect on acid base, just one's more basic than the other. It would be like going from a difference of pH 5 to pH 8, let's say. And since we know that it's logarithmic, from pH 5 to 8, that's actually not as much of a change it as it is from going from 1 to 3, for example. It's just slightly different, since that's how logarithmic scales work. Now, that's sort of how it works. So even if you neutralize some acid, the base, has similar acid-base properties, and it sort of helps to mitigate the effects of that. Now, the way it works is that strong bases are converted to weak bases, and likewise with strong acids. So here we have a weak acid, we add a strong base, and we get a weak base and neutral. And similarly here, if we add acid, we get a weak acid and neutral. So we convert strong to weak. And weak acids and bases will have less of an effect on the pH than strong acids and strong bases. So that's sort of how it works. It converts. So here, let me sort of go through this sort of. So if let's say we had ethanoic acid to H, and this is in equilibrium with H plus H3COO minus. Now, if we add acid, so this following equilibrium is maintained in a buffer solution. Now, it's pretty clear that if we add H plus here or any kind of acid to it, it's pretty clear that this equilibrium will shift to the left side, and therefore you essentially remove this strong acid and convert it to a weak acid. Now, it's not totally clear for a weak base. However, remember that acids will react with bases, and therefore, because that's true, it will shift to this side, since acids will react with bases. and this will go down. Acids will react with bases, and this side is preferred here. Now keep in mind that since this is both weak, and we have Ka times Kb equals Kw, but we know that for a weak base, that these aren't not too different. Like, it's not the difference between, I don't know, like, and it's not like that kind of difference. It's more like 1.0 times 10 to the negative 9 and 1.0 times 10 to the negative 5, which, although those are orders of magnitudes that are obviously very different, however, they are much higher than, they are much bigger than Kw, which is important to note here. And therefore, they will affect the pH of it. However, going from one to the other will not cause the pH change to be nearly as drastic, is sort of the point. Now, how do we design buffers in the real world, right? So, firstly, I think we should, let's rearrange this Ka expression here. Let's rearrange Ka. First, let me erase everything here. Select all, delete. Let's rearrange Ka. So we have this expression for Ka, and we can just rearrange it to this. So we just divide it by H plus here, and we get that. And we know that for in a buffer solution, or one way to make a buffer solution is that HA equals A minus. So remember, A minus is the conjugate of HA. And if these equal each other, this fraction is 1, which also means that this fraction must be 1 as well, which therefore would imply that Ka equals H plus, right? This implies this. So to make a buffer solution, you can directly mix HA and A minus in a 1-to-1 mole ratio. Or you can mix HA in a strong base in a 2-to-1 mole ratio, or mix A minus in a strong acid in a 2-to-1 mole ratio. The idea here is always the same, that you will always end up getting a 1-to-1 ratio of weak acid to weak base. Now, for the 2-to-1 bits, it's easy. It makes more sense if we show the reaction. So here we have 2 and 1. Since this is the limiting reagent, only 1 mole of this will react. This will go to 0. 1 mole of this will react, and we get 1 and 1 mole here. Remember that this ionic salt here will be disassociated in water completely, and we get 1 mole of acid to 1 mole of its conjugate base. And then likewise, that's also true here. If HA and K, if this is not true, if HA is not equal Ka, but it's close, you can adjust this accordingly. You can adjust the ratio to get what you want, more or less. Now, let's actually go back here. We have this expression here. What we can do is, I want to derive an equation here. For those that take some of the option topics, you'll see why I'm doing this, but for now, this is another way to calculate the pH of a buffer solution. So, we know that Ka equals H plus A minus over HA. Now, I can write this out as H plus times A minus over HA. Right? Now let's take the log of both sides. So we get that log Ka equals log H plus times A minus over HA. Right? Now, because we know from the rules of logarithms, we can further split this up into... Now, remember that pH equals negative log H plus, and that pKa equals negative log Ka. Now, if I were to multiply everything by negative 1, let's do that. Well, let's keep that in mind, and this will end up becoming negative, let's say negative pKa equals negative pH plus log H, no, A minus over HA. Oops. A minus over HA. And then we can do a bit of rearranging to get that pH equals pKa plus log A minus over HA. And we are done. This is the equation that we've derived. It's called the Henderson-Hasselbalch equation. And you can use this to calculate the pH of a buffer solution. So the pH of the buffer solution is equal to the pKa plus the log of these concentrations that are in the concentration of that over that. You can further rearrange this to log A minus log HA, but this is usually how it's written in textbooks and formula booklets. So with that derivation complete, that's sort of another way you can calculate the pH buffers. And this is particularly useful if you're not given something that's nice. You can always just resort back to the Henderson-Hasselbalch equation, and you can go from there. Now, lastly, the last thing I want to talk about today are indicators, chemical indicators. So, pH indicators we discussed. Basically, we're just going to discuss choosing indicators. So, a pH indicator is a chemical that changes over a narrow range of pH. You can assume that the pH range is approximately 2 units of pH, and you can assume that the pK is equal to the pH at the equivalence point. Now, remember, we can use sort of the logic of acid-base equilibrium to sort of get there. Remember that at the equivalence point, HA, at the equivalence point, there's all of this and none of that. Back. So this is 0 or whatever. Well, you can explain that. Explain some of the. Okay, I need water. You can explain those assumptions using acid-base properties. You can using some of the acid-base chemistry we just discussed. That, however, I don't feel like in the mood of doing it, but you can assume it covers. You can assume the range of the indicator is the pK plus or minus 1. And here's a table of common indicators. All you need to know for choosing the right indicator is that you need to know the pH of the equivalence point, and then you can remember that remember that pK is about the pH where the color change will occur. So, for example, if we did for hydrochloric acid and sodium hydroxide, whose equivalence point pH is around 7, bromomethyl blue would be a suitable choice here. Phenyl red wouldn't be too bad a choice either. And that's sort of how you choose an indicator for a titration, an acid-base titration. Thank you very much.